Okay, let us go for the next part and the definition of limit of a function. So this chapter now is limits of a function. And again, we separate the various good behaviors that we want to isolate. And the first is the definition of a convergent function. This time I want to give you first the rigorous definition and then to discuss it, okay? Because previous discussion was already quite heavy. Now we go to the precise point and then we extend it and explain it. Okay, so as usual we have a subset E of R that will play the role of the domain of a function we are interested in. Then I take x bar to be an accumulation point of E. Then F goes from E to R, the function we want to study, and L, a real point. Then it is said that the function f and one can say tends, goes, converges to L as x, tends, as x tends, or goes, in this case not converges, to x bar, if, okay, I give you two definitions. The first definition is conceptually simpler, which is the metric definition, the so-called. So let me write it as metric definition. If for every epsilon, as you suspect, larger than 0, there is delta larger than 0, such that if x is in E and x is distant from x bar less than delta and it is not x bar, then the distance between f of x and L, f of x and L is less than epsilon. Okay, this is the easiest definition you can find. And let me explain it by a picture. As usual, let me portray the graph of the function we aim at studying. And so here we have this function here, and suppose that this is x bar here, and so there is something strange here. Okay. Here there is x bar. In x bar, the function, for instance, is here. And let me go further with this. graph in this way, like this. And so L, in this picture, we have the candidate L, which is here. And just to make things a bit more complicated but more complete, here I put f of x bar. So that has really nothing to do with L. It is completely different. So, but this is a good picture for this situation. As x tends, so as x tends to x bar, the function f tends to L. Why? Because let us consider, as in the case of sequences, epsilon larger than 0. Epsilon larger than 0 around L gives you the following stripe, whose width goes from L minus epsilon up to L plus epsilon. Okay, this is the stripe. So I'm saying here the following. For every epsilon, so in particular for this epsilon here, there exists another number delta, such that if I am delta close and not x bar, then f of x is epsilon close to L, which means that there is a spherical neighborhood of x bar. There must be a spherical neighborhood of x bar here, such that the points f of x corresponding to the x in these spherical neighborhoods fall into the horizontal stripe. And this is a good choice. X bar plus delta here, x bar minus delta. And you see that here the image of this neighborhood here is well inside the orange stripe. And this is the idea. Stop. So now the question is, okay, if you did not understand this picture, try to do it by yourself. Go back in the lecture and recover it. This is extremely important because this is the idea of limit, at least for a convergent function. Okay? This is the basic, elementary idea. First, a remark. And I write here a small box here. And the remark says, what is the role of f of x bar here? The answer is extremely simple. F of x bar has no role at all. At the point that it could also not exist. So the function f could not be defined x bar. X bar must be a point of accumulation of the domain, but it does not need to belong to the domain. Okay? And now I discovered it goes to the rubber by itself. Haha, it's not a mistake of mine. So it could even not exist. F of x bar never enters in the definition of limit. Okay? So it has completely no role. This is why I put here in this absolutely nonsense point here. Nonsense in the sense that it has no relationship with the limit. F of x bar is not here in the definition. Here we just have f of x, but for x, that cannot be x bar. So when you are computing a limit of a function for x going to some x bar, you can completely forget about f of x bar. It has no interest at all. When we will study continuity, it will change. The definition will change and f of x bar will be extremely important. But here, for the notion of limit, it has no role at all. Okay, put it in mind. So this is the first remark. The second remark opens the road towards a more interesting, abstract, and also generalizable definition of limit. What is this definition? It is the following here. When using epsilon, what we constructed here is a stripe, and this stripe is a neighborhood. We can say that this stripe, horizontal stripe, is a neighborhood of L. Okay? We can call it V, for instance. This is a neighborhood of L, so we can write here V, which is an element of the set of all neighborhoods of L, according to our previous definition. On the other hand, here, this guy here, this is a neighborhood of x bar. And this is x minus delta, x plus delta, and we can call it u. Which is a neighborhood of x bar. Now we can give a second definition of a limit that I will call topological definition, but metric or topological are just words, okay? Focus not on my words, but on the definitions. So the second is the topological definition. Let me say, to clarify, the first definition is good, is finished, but I'm interested in giving you another equivalent definition, which is the following. Instead of saying for every epsilon larger than 0, because epsilon is useful in order to define a neighborhood here, I say for every neighborhood of L, for every V neighborhood of L, there exists U neighborhood of x bar such that for every x, which is of course in E domain, but also in this U, and which is not x bar, you have to remember all of that in order to give the correct definition of limit, then the image of this x is in V, the neighborhood we chose for L. This seems to be more complicated, but it is not. It's much more simple, and we can also give it another form, which is probably the shortest one, and in red here, or equivalently again. This is my favorite definition of limit. For every V in UL, there exists a U in UX bar such that the image of this set E intersection U minus x bar is contained in V. That's really wonderful. Why is it wonderful? So let me simply copy here and adapt to what I want to say. So I have to cancel a bit here. Let me cancel epsilon and so on. Let me cancel the stripe. Let me cancel here. I am saying the following fact. I'm reasoning about neighborhoods, so I really don't need anything to be spherical. I exaggerated a bit, but okay, good. I just have to put a vertical axis here. This is a vertical axis. And again, I have L, which is important. I also have f of x bar, which is not important at all, but I keep here. This is L. So look at the last definition here. I'm saying that for every neighborhood of L, so let me consider a stripe, but it is every neighborhood, so I'm not obliged to make it symmetric. For instance, this is a good stripe. And then the definition states that there exists a neighborhood of x bar such that this neighborhood, except possibly the point x bar, which is not interesting, then this neighborhood is mapped by f into V. In other words, the image of this neighborhood is contained in V. How can I find it? Okay, just look at this. Look at this picture and try to isolate the set of the x, of the variable x, that falls into this stripe. So take where this stripe starts, where it ends. And so, like in a magic, what you have here is a neighborhood of x bar. It is not symmetric, but it doesn't matter, because I'm not talking about spherical neighborhood. I'm talking about general neighborhood. So in our definition, this is V, and this is U. So pictorially, it is much, much more simpler. Much simpler, okay. Okay, and this definition that I call topological, I will try to explain why later, has another advantage too. By using this definition, we can extend it, and we can extend the notion of limit not only to the case of divergence, but also to the case that x goes to plus or minus infinity. In order to do that, we have just to define what is a neighborhood of plus infinity and of minus infinity. Okay? So the last definition is more abstract. So at the first sight, probably you don't like it, but then you will love it. So this definition is more abstract. But it generalizes to cases of divergence of f and also to cases when x goes to plus and minus infinity. Okay? Before doing that, I want to add here a line that I forgot, but it is just a simple, but it is important. And the definition I gave here, I gave the same definition 3 times, but it's always the same, is denoted symbolically by one writes lim x going to x bar of f of x equal to L. The writing you know very well. However, I have to define it, okay? This writing here corresponds to this mathematical statement here, which is completely equal to this mathematical sequence statement here, which is completely equal to this definition here, okay? Choose your favorite between the three, which is the third, and then think in terms of this definition. So just one word, why metric and why topological? When I say metric is a word that in mathematics is linked to the idea of distance. Okay, so here I say metric, and indeed in this definition there are two distances. First, the distance between f of x and the limit. Second, the distance between x and the base point of the limit x bar. Okay, so we have this epsilon and delta that are numbers, are distances. When you go from metric to topologic in mathematics, what you mean is that you are losing the distance. You are preserving a sort of idea of vicinity, of being neighbors, but you cannot quantify how much you are neighbors. So here you say that there is a neighborhood of UL, but how large is it? You don't know. You don't know at all. But for every neighborhood, here there is another neighborhood, but you lost every notion on how is it close. This seems to be a loss, an important loss, but it is not an important loss. On the other hand, it gives us the possibility to use the same definition for L equal to infinity and also x bar equal to infinity, because for plus and minus infinity, you have no notion of vicinity. You don't know how far are you from plus infinity. You are always infinitely far from plus infinity. If you are 1 or if you are 1 billion, it doesn't matter, your distance from infinity is always infinite. But if you don't use distances and you use just neighborhoods, you can use the same definition, provided that you find a suitable definition of neighborhood of infinity. But it is not your task, because great mathematicians made it before us, so I give immediately the definition. So, extension of the definition, the last one in particular, to the case L equal to plus minus infinity and x bar equal plus minus infinity. So I immediately give you the definition, which is the following. Definition. So a set a subset of R that contains a right half line, which means namely a set of the type K plus infinity, is called a neighborhood of plus infinity. This means very simply the following. You have a real line, and then you take K here, and here you have a half line starting from K, getting to plus infinity. So every set that contains this subset k plus infinity is a neighborhood of plus infinity. And as again, a notation, as before, again, we have this elegant u plus infinity is the set of all neighborhoods of plus infinity. This is the set of the subsets of R such that U is a subset of plus infinity. This is one definition. Another definition is the following. The symmetric one for minus infinity. Sorry. A subset of R that contains a left half-line, namely a set of the type minus infinity minus k, is called the neighborhood of minus infinity. Okay? And in a completely analogous way, we have the notation we say u minus infinity is u in R such that u is a subset of minus infinity. Okay? And so here, so another notation which is quite important, and it is just a notation to our purposes, but I will define the so-called extended real line. Extended real line means that we have the real line, R, together with the points plus infinity and minus infinity, that I write here as plus minus infinity. This here is usually denoted by R bar. So this is the real line, plus, so with, in addition, the points plus and minus infinity. This is just a symbol for us. I will not introduce a strange operation on that, but why it is comfortable. So, by using it, we can give a general definition of limit. Which is the following. We say that E subset of R, X bar is a point of accumulation of E. No, let me introduce. Okay. Sorry. There's a passage when using point of accumulation because I have to define when plus and minus infinity are points of accumulation. So, definition. So, it is more or less a convention. If the subset E of R is not upper bounded, we say that plus infinity is a point of accumulation of E. Notice that this is not inside our previous definition of point of accumulation, because we're starting from the fact that points of accumulation must belong to R. Okay? In this case, plus infinity is not in R. But as it is exactly like we did when defining the supremum of a set is equal to plus infinity if such a set is not upper bound. It is exactly the same thing, okay? But it is a convention, and we also say that plus infinity, the symbol plus infinity, belongs to the E, okay? And exactly the same thing for minus infinity. So for sets that are not lower bounded. So if this is another convention, which is specular to the previous one, but I write, however, here. If E subset of R is not lower bounded, then we say that minus infinity is a point of accumulation of E, and we also say that minus infinity belongs to derived set of E. It's a point of accumulation. And now we go to the definition I was about to state some minutes ago. So we say the definition, this is the general definition of limit. Limit of a real function of a real variable. Okay. However, we start from saying that subset of R, X bar, points of accumulation in E. In this case, I can also include plus or minus infinity. In order to be aware of that, I write that D of E is not a subset of R, but is a subset of R bar. We include the possibility of having plus and minus infinity. L is an element of R bar 2, again with plus or minus infinity as possible options, and F from E to R. Okay? We say F tends or goes to L as X tends to X bar, and write that for every V in UL, that can be also plus infinity, there exists U in UX bar such that F of E intersection U minus X bar is contained in V, exactly the previous definition. And what we write is that lim for X going to X bar of F of X equal to L if this is true. And this is the definition. This is completely topological, completely abstract, completely general. If you get acquainted with that, it is extremely clear. So I invite you to focus on that, even though probably you are not familiar with that. You have to learn something in this course. You cannot go always with what you already know from high school. So please focus on that and try to understand that. And of course, there are metric versions. Metric versions are the following. First, lim for X going to X bar of F of X is equal to plus infinity, and X bar is in R. Okay? So F is diverging positively, so we have to say for every K in R, there exists x bar is in R, so there exists delta larger than 0, such that for whenever x is not x bar, closer than delta to x bar, and x in E, then f of x larger than k. Okay? This is the definition as f diverges when x goes to a finite point. Second, limit for x going to plus infinity of f of x is equal to L when L is real. So first we have the neighborhood of the limit of L. The limit is finite, so we write for every epsilon larger than 0 there exists k in R such that whenever x in E and x larger than k, then the distance between f of x and L is less than epsilon. Okay? Notice here we are mixing the two definitions, the notion of plus infinity and L. I write you the final one, and then lim for x going to plus infinity of f of x is equal to plus infinity. Here, first think of the limit, which is plus infinity, so for every x in R, then there exists m in R, such that if x is in E, x larger than m, then f of x is larger than k. Very easy. As a homework, following definitions, the remaining ones. So, lim for x going to minus infinity, so like x going to x bar, f of x equal to minus infinity, x bar in R. Then lim x going to minus infinity, f of x is equal to L, with L real number. Then limit x going to minus infinity, f of x is equal to minus infinity. Then lim x going to minus infinity, f of x is equal to plus infinity. And the last one, lim for x going to plus infinity, f of x is equal to minus infinity. So you see there are many definitions. Here we have 5, 3, 8, and there is another one for everything convergent, which is 9. So we have 9 definitions of limit according to the situations, but they are all included in this one. This is why I like it. It's a unified definition, but you pay the price. The price is to be more abstract, and also the price to make an effort to understand better things. I stop here, and then we go further and further.